welcome to Vodcast 16.1. In this Vodcast, I will provide an introduction to the universe and the Big Bang Theory. By definition, cosmology is the study of the universe. Do not confuse this with cosmetology, which is the process of making people beautiful. In cosmology, we have a very important unit of measure, and that's called the light year. A light year is a unit of distance that makes sense on a cosmological scale. And by definition, a light year is the distance light travels in 1 year. If you wanted to know that distance, it's about 10 trillion kilometers, but that number's so big our minds can't even really grasp it. Let's take a look at an example that helps you conceptualize the light year. Betelgeuse is a well-known star in the night sky. On any given night, there might be two objects in the sky that appear red. One of those objects is often Mars, and the other object is the star Betelgeuse. Betelgeuse is about 520 light years away from Earth. What's really cool about that is if you go outside at night and look at Betelgeuse, you're not seeing Betelgeuse as it is now. You're seeing Betelgeuse as it was 520 years ago. Because that light that your eye is detecting took 520 years to travel across the universe. It's very important to note that all light travels at the same speed. I don't care if we're talking about visible light, ultraviolet light, infrared light, X-rays, gamma rays, whatever. The speed of light is 186,000 miles per second, or if you prefer, 300 million meters per second. So the point is, light travels fast, but it always travels at the same speed. An interesting fact about Betelgeuse is that it's a red supergiant star, and it's a very good candidate to go supernova. Now let's suppose Betelgeuse explodes today. The light from that explosion will take 520 years to reach planet Earth. But if Betelgeuse went supernova and exploded 520 years ago, the light from that explosion could reach us this very minute. At this point, I'd like to shift the conversation to the Big Bang Theory, because when we talk about cosmology and the study of the universe, it's nice to know the scientifically accepted mechanism for the formation of our universe. The Big Bang Theory describes the birth, evolution, and fate of our universe. A very long time ago, the universe was once confined to a ball that was supermassive, extremely dense, and extremely hot. Over billions of years, that ball has expanded. To be more specific, the birth of our universe occurred 13.8 billion years ago. And at that moment, the universe began expanding rapidly in all directions. To this very day, the universe is still expanding, and on the slides to come, I'll go into more detail about that. It's very important to know that the first two elements to form were hydrogen and helium, the two lightest elements. As we'll learn in a future podcast, the heavier elements like carbon and iron and gold were formed inside of stars. To understand the Big Bang Theory and the expansion of the universe, there's a very important concept that we have to understand, and that's the Doppler Effect. The Doppler Effect is the change in wavelength due to motion. I want to show you a really brief video that demonstrates this concept very well. As that train approached the observer, the pitch of the whistle got higher, because the sound waves being emitted from the train were being compressed. But as that train passed the observer, those sound waves got stretched, and that's what caused the train whistle to have a lower pitch. Now what's important to note is that the Doppler effect works very well for sound waves, but it also works for light waves. To explain, if a light source is moving away from you, we'll see what's called a redshift. Specifically, the light will have a longer wavelength and it'll appear redder. So just keep in mind that redshift means the wavelength for light was shifted towards the red side of the visible light spectrum. Now, if a light source is moving towards you, the wavelength of that light will be squeezed. And what you'll observe is a shorter wavelength and light shifted towards the blue side of the visible light spectrum. I'd like you to focus on the image shown on this slide. If there's no motion between the observer and the source of light, you would see the standard spectral line shown at the top of this image. But now, let's suppose the observer stands still and the light source starts moving away from the observer. What you would now see are the spectral lines shown in the bottom portion of this image. Notice that all of the dark vertical bands were shifted to the right, or more specifically towards the red side of the visible light spectrum. This red shifting will occur anytime a light source is moving away from you. If the light source were to have been moving towards you, we would see a blue shift, meaning that all those black vertical lines would have been shifted slightly left of the standard spectral lines. So what does all this have to do with the Big Bang Theory? It's very important to know that most galaxies exhibit a red Doppler shift. So when we look at galaxies through telescopes, the light coming from these galaxies is redshifted. This tells us that most galaxies are moving away from us. What's also important to note is that the further a galaxy is away from us, the greater the extent of the redshift. These faraway galaxies exhibit a greater velocity as they move away from us. Now, to conceptually understand what's going on with all the galaxies, I'd like you to consider this example of raisin bread dough. Let's suppose Earth can be represented by this raisin here, and this is the raisin bread dough before we start to bake it. The raisin to the bottom left side of us is 2 centimeters away, and the raisin to the bottom right side of us is 6 centimeters away. As we bake the raisin bread dough, the dough will expand. So now if we shift our attention to picture B, and keep in mind where the Earth raisin was, we now see that the distance to the bottom left raisin has doubled from 2 centimeters to 4 centimeters. And the distance to the bottom right raisin has also doubled from 6 centimeters to 12 centimeters. So the bottom left raisin has moved an additional 2 centimeters away from us, but the bottom right raisin has moved an additional 6 centimeters away from us during the very same time frame. This redshifting and expansion was discovered by Edwin Hubble in 1929, and Hubble's law states that the recessional speed of galaxies is proportional to their distance. The further a galaxy is away from us, the faster its recessional speed will be away from us. But the key point here is that the expanding universe accounts for all the redshifting that we see when we look at other galaxies. Okay, that concludes this video podcast. In our upcoming vodcasts, we will consider stellar evolution and we will study Hertzsprung-Russell diagrams.